This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So as Sumeet is setting up, we're going to have a lot of exciting talks today. So the first talk today will be by Sumeet Khatri. He just moved to Virginia Tech, a couple of months ago, but he was in Jens's group, so he's going to talk about online learning and quantum processes.
All right, thank you very much, and it's nice to be here. Nice to have this opportunity, and I'll be talking today about online learning of quantum processes. So this is joint work with Asad, Matthias, and Jens. They were the learning theory experts in this, and I was happy to be the learner in this. Okay, so far what we have seen for the most part in this conference so far is a sort of model of machine learning that kind of goes like this, right? So you have some label data and you have the corresponding labels. And what you do is you take all of this bunch of data, this is your training data, you put it into some machine learning algorithm, and then that algorithm will spit out some model, right? And this model should then be doing well at predicting the values of the labels for new and unseen data points. Right? And once this model has been defined, it's fixed, right? So that's how it works, and we would all know this as being called supervised learning, right? So as I mentioned, supervised learning will have a distinct training and testing phase. And in particular, it's a kind of batch learning scenario. So whatever hypothesis you come up with for this unknown function that maps the data to the labels, it's based on taking in all the training data at once and then learning the model based on that data. On top of that, the data is assumed to be IID. And the goal here, as I mentioned, is to obtain good generalization bounds or good prediction performance. And the way we sort of quantify this kind of prediction and generalization is using the PAC pack learning framework, which was sort of initiated in the early 1980s. But it's interesting to note that already in that same decade, in the 1980s, people started thinking about a different kind of machine learning model, and this is called online learning. So in online learning, what you're doing is you're not taking in, there's no distinct training or testing phase. What you instead do is you have a sort of running hypothesis for your unknown function, and you continuously update this as you receive new data. And to me, this is an appealing concept. Because here, in this case, the data is given sequentially, and on top of that, it can be non-IID, and it can also be given to you adversarially. So this is an appealing idea. But now, in this kind of scenario, how is it that we should quantify learning? So the way we quantify, or the way it's often quantified in the setting of online learning, is this notion of regret. So the way this learning procedure goes is the learner will, so the data source will give the learner some data point. The learner will have had some prior hypothesis at time t-1, which at time t, it updates to its new value based on the feedback that it received in the previous round. Right? So now what the learner will do is that it will spit out a new data point. It's sort of new predicted value. Give it back to the source, and the source will provide it with the true data point or true label or some form of feedback. And it will use this feedback, the learner will use it to update its hypothesis to some new function f at time t+1, which it will then use to evaluate what happens on the new data point that the source gives it. Right? So what we can do is this kind of procedure with the learner and the source can proceed for, say, capital T rounds. And at the end of the T rounds, you can calculate the total amount of this loss. Right? So there's going to be some loss associated with the learner's decision. And what we can do is we can compare this total accumulated loss over the T rounds with the loss that it would have incurred had it had all of the data points to look at once. And it could make a decision based on having seen all of the data points at once. So pretty much exactly like what you would have had in the batch learning scenario. And that's what the second term corresponds to. So the optimal choice of the function that it could have picked had it seen all of the data points at once. And people call this the regret because the higher this is, the more you might think, oh, I wish I could have picked that particular function instead, right? Instead of the ones that I actually picked. So people in machine learning literature call this quantity the regret. So this is the figure of merit that we're going to be looking at. And the actual physical problem that we consider in our work is the learning of quantum processes. So oftentimes we think about learning quantum states, and quantum states in the end are always going to be generated by some process. Right? So to me it makes sense that we have a learning scenario where we actually care about learning the process itself. And in this kind of scenario, what one might imagine is that you have the ability to prepare some states, maybe some simple states. You can send it through your unknown process, which I sort of symbolize with this blue cloud. Your system comes out and you do a measurement. Right? And now the goal is to essentially learn this kind of expectation value. Right? So you want to learn observables of your channel, and your channel observables are going to be of this form. Right? So the actual functions that we care about, sort of mapping it back to the general scenario that I presented on the previous slide, is a function of this form. And what we can do is we can take this form here and write it in terms of the Choi matrix of the channel. Right? So both the input state and the observable appear in this way. And then we take the inner product of that with the Choi matrix of the channel. Right? And the Choi matrix, if you might know, has this form. And in particular, this is very close to sending the channel through 1/2 of a maximally entangled state, but it's not quite that. And this is kind of an important point. Where here, what we do is we send it through 1/2 of the unnormalized maximally entangled state, and we call that the Choi matrix. And that is really inherently the quantity that, or the operator that appears here in this expectation value. Okay. So this is a kind of scenario where we can think about channel observables, but more generally we might have a channel observable that is of this kind, where instead you have the ability to prepare a state row with some auxiliary system. You send only 1/2 of that bipartite state through the channel, and then you do a measurement on the joint auxiliary system and the output system of the channel. Right? And this models a scenario where you have some sort of memory. And we can describe those in a very similar way. So when we have observables of that kind, we can again think about them in terms of an inner product with the Choi matrix and some quantity E. And this operator E is the channel version of a POVM element or some observable. And rather than just being between 0 and identity, in the case of channels, what you end up having is that this E should be positive, of course, but it's going to be less than or equal to this kind of tensor product with some state sigma and identity. So the first tensor factor is the input space, and the second one is the output space. And now our regret is just as it was before. And the learning procedure itself, so just mapping the general scenario onto what we have now, is the learner is tasked with coming up with good hypotheses for the channel, and we can think of the hypotheses as themselves just being the Choi matrix of the channel. Right? So at each round, the source will give it some channel observable, and the learner's task is to estimate, come up with a good estimate for this expectation value, this inner product. And as feedback, based on the guess of the learner, the source will give it some loss, and this loss is just like the sort of L1 loss that I showed here. Okay, and the regret is this kind of right here. So here we might not necessarily want to minimize over all CPTP maps because it might be not possible to get good regret bounds when we look at arbitrary CPTP maps, where we might want to make some assumptions, and indeed that's what we do. Make some assumptions on the form of this channel. And the goal of our work was to essentially look at this quantity and to see if we can come up with good regret bounds. And what do we mean by good? What we mean is that regrets should be upper bounded by something like this. So here you have the square root of t, which is the number of rounds. And we also wanted it to be scaling not too badly with the dimension of the input system of the channel. So we would ideally want something that's like a polylog of d, right? So if you imagine that d is 2 to the n, where n is the number of qubits, then this would be sort of like poly n. So this is what we aimed, and we wanted to see for what classes of channels could we do online learning with regret that scales in this way, right? And the nice thing about our framework is that we can actually generalize this to not just a channel, which is like a single time process, but we can also generalize it to multi-time processes, and to processes in particular which have some memory corresponding to non-Markovian evolution. So this is quite nice. And the interesting thing is that the only thing that will change in this kind of scenario is the form of the expectation values themselves and the kind of mathematical constraints they should satisfy. Okay? But in the end of the day, whatever those constraints are, and I haven't written them, the expectation value itself will just be an inner product with the Choi representation of the evolution or of the process and that observable, whatever it is. Okay? So here I've drawn this in the case where you can actually make 3 uses of the channel, 3 queries with like adaptive queries. And here, again, you just get some kind of expectation value that's this kind of inner product where now you have the Choi representation of the channel tensored 3 times because of the 3 uses. So it looks very similar to the state case, because if you had 3 copies of the state, you would also just have here row tensor 3. But now instead of that, you have the Choi matrix. And here, if you have a blue process, which is the unknown thing, then again, you'll have a similar inner product, where this is the Choi representation of this whole process. Okay, so I'm just going to flash some of the results that we got. And we considered, in particular, 2 classes of channels. So one of the things I also did not mention is that on top of looking at this quantity called regret, it also makes sense to look at this a quantity called the number of mistakes, right? Because you could imagine that over this number of rounds, the learner will make some number of mistakes. And here also we would want the number of mistakes to not be so bad. So we would want sort of polylog in the number of qubits, number of mistakes. And we can come up with 2 classes of channels for which we can do this. And we can also prove that for arbitrary channels, you will in general just make an exponential number of mistakes. So we really do need some structural assumption on the channels. And the structural assumptions that we make are 2 of them. So the first assumption is that either the channel is within the class of G-gate channels. And by G-gate channels, we mean that it's some channel on n qubits, which is composed of at most G 2-qubit channels. So you can think of some kind of brickwork circuit where the elements of the circuit are composed of 2-qubit channels, and at most G of them. The second class of channels that we look at is the Pauli channels. And here we can come up with a regret bound exactly of the kind that we would want, and what I mentioned on the previous slide. So we get that square root of t dependence and the n dependence. And I didn't mention that the square root of t dependence is a kind of common thing that you would get even in classical online learning. So this is the kind of standard desired thing that you would want in online learning, because what it means for the regret to scale sublinearly in this way with respect to t, what it means is that the average regret can then go to 0, because ultimately you want the regret to get smaller and smaller. In general, that won't be possible, but if you look at the average regret, so if you take the regret and divide it by t, as long as the regret itself scales with the square root of t, then the average will decay to 0. So the square root of t is something that just comes from standard online learning algorithms, and I'll describe what these algorithms are. And it's really the linear dependence on n, which I would say is the interesting part of the results here. So by making the assumption that the unknown channel is Pauli, and also similarly that it's a G-gate channel, you can get this kind of nice dependence on n. Either it's linear or it's like logarithmic. Yeah, so I'm not going to have time to go through all the results or like all the particular ways in which we can generalize these results. But one interesting thing to point out is that because Pauli channels are just convex combinations of single sort of unitary Pauli channels, our results actually can generalize to arbitrary convex combinations of known channels. And hopefully that will be clear when I show the proof for the Pauli channels. And we can also say something about non-Markovian processes, which I sort of mentioned on the previous slide. And we also have computational complexity lower bounds, which I haven't shown here. But it's all in the paper. Okay, so at this point, I also want to mention that we are not the only ones to have looked at online learning in the quantum setting. So some of you might already be aware of this paper on online learning of quantum states from some number of years ago, from Scott Aronson and others. And there they also get a regret bound that's similar in the case of states, right? And now the task is very much the same. So what you want to do is you want to measure expectation values of the unknown state, and you keep continuously updating your hypothesis for the state, right? And they use a particular algorithm. They have 3 of them, but I'm highlighting this particular one here, called the matrix multiplicative weights algorithm. So essentially what you do is you start from a state of complete ignorance. So you start from a maximally mixed state as your guess for the unknown state, right? And as you go through this procedure of getting feedback, you can continuously update your hypothesis for the unknown state. And you do it in this particular way. You do these kind of exponential updates. And essentially what that amounts to is that at each round, you're essentially providing a Gibbs state as an update. For those of you who might be familiar with that. All right. And for this, you can prove a regret bound that goes like this. So it has that, So in eta here is the learning rate. So now you might wonder, okay, so if this already exists, for our process case, why not just do this for the choice state, right? So that's a fair question. So first of all, what I can say is that what we actually want to learn is this expectation value, where here we don't actually see the choice state, but we see the unnormalized choice state. But what we can do is we can instead write this quantity in terms of the choice state, but then we incur a cost of this dimension factor here, right? Where we should remember that this d is in general 2 to the n if our input space dimension is, input space is on n qubits. So in general, if we were to do the choice state thing, we wouldn't necessarily get good regret bounds just by applying the choice state idea. On top of that, the choice state also satisfies this constraint so the choice state is a bipartite state, and if you trace out the second tensor factor corresponding to the output space, the state should be maximally mixed. So now the problem with this is that this constraint won't necessarily be satisfied in this kind of matrix multiplicative weights algorithm. So this matrix multiplicative weights algorithm only ensures that your hypotheses have trace 1. They won't necessarily guarantee that this partial trace constraint is satisfied. So even from that standpoint, applying the choice state idea is not necessarily enough. So to emphasize, our task is to learn the Choi matrix, and what I'll do now is describe to you go a little bit into the proof of how we get our regret bounds in the case of Pauli channels. So our result for Pauli channels is over here. And just to remind, Pauli channels have this general form, where P here is essentially the unknown probability distribution. And these PZXs are the Pauli, n-qubit Pauli operators. All right. So what I want to now do for the remainder of this talk is go through a little bit of the proof ideas here. And essentially, the idea behind the proof is we want to leverage classical algorithms that can essentially learn this probability distribution in an adaptive way in this sort of online setting. Okay, and how do we do that? So we make use of this algorithm, which is called the multiplicative weights update algorithm. Right? So the motivation here is that you have a choice between D decisions, and what you want to do is you want to make the best decision in each round. And in each round, based on your decision, you will incur some cost. So what you can do in terms of making your decision is you can have a probability distribution over your D decisions. And after each round of incurring some cost, you can update this probability distribution over your decisions. Okay? So what we do is we start with some initial weights corresponding to each of the decisions. And they're all set to 1. and then you normalize this so that you just get a uniform distribution over all of your decisions. Right? Now, as you start receiving in this feedback loop the various cost vectors associated to your decision, what you can do is you can update the weights according to that cost. Right? So decisions which don't lead to a very good cost will start to get lower and lower weights, and you can use that then to update your probability distribution in this way. Right? So you update your weights in this way, and then you renormalize to get your probability distribution. And so this is a well-known algorithm for online learning in the case of probability distributions. And the regret bound that you get looks like this. Right? So if Q is an arbitrary vector of probabilities, this is the expected sum of the losses that you'll incur. And essentially, this holds for arbitrary Q, so it holds for the Q that will minimize, in hindsight, the losses that you incurred, the total number of losses that you incurred. Right? And here we see that the nice thing here is that you already have, from the classical result, this log D dependence. And that's what's going to ensure that we also get a similarly nice dependence on the number of qubits in our case, because for us, D is going to be like 2 to the 2n. Okay, so how are we actually going to make use of this algorithm? Essentially, what we're going to do is, so there's a lot of stuff going on here, but I'll go through it carefully. So remember that the task here is for us to learn the Troy matrix of the unknown Pauli channel. And we're going to assume that we know that it's a Pauli channel that we need to learn. And so all we need to do is learn the corresponding probabilities in this way. Right? So what we want to do is we want to map our learning problem into the problem of multiplicative weights. So all that amounts to is picking correctly how to define the cost vector, and also how to define the probability vector that we actually learn. So the probability vector is clear. So all we do is we want to actually learn the Pauli error rates of our unknown channel, and we plug that into a Troy matrix form. Right? And then we define our cost vectors in a particular way. And what we do now is our unknown Pauli channel has this as its Troy matrix, where Q is basically, the unknown arbitrary vector Q here. Okay? So once we have all of these tools, so what we do is, so our cost vector is directly related to essentially the expectation values or the losses that we actually receive from the source. Right? So once we've mapped the problem onto the matrix multiplicative weights algorithm, we can make use of that along with this lemma, which basically tells us, it's a kind of a technical lemma that we need in order to actually make use of the multiplicative weights update algorithm, but it's not so bad. Then we can see that with these choices of the vector m, we get precisely the form that we need in our multiplicative weights update algorithm to actually make use of that algorithm. And then what we can see is that the actual regret that we care about, which is this quantity, will actually be precisely equal to essentially the quantity here. Right? So once we have that, we have the bound that we want. And this L is actually just the Lipschitz constant of the loss function, this capital L. So if we think of just the usual L1 loss function, then this L will just be equal to 1, but we can prove this for general loss functions, and all we care about is the Lipschitz constant of that. And now, as long as we set the learning rate, eta, to be appropriate, then we'll get the square root on t dependence and also the n dependence that we want. Okay, so I'll end it there. Essentially what I wanted to try to convey is this sort of different style of learning as opposed to supervised learning called online learning, where instead of taking all of your training data in one batch and then learning a model and then testing it on new data, what you do is you update your hypotheses sequentially, right? And what we set out to do in this particular project was to see, okay, can we make use of known algorithms, and under what assumptions on the channel can we actually achieve good online learning performance? Right? So we can prove that for general channels this is going to be difficult, but as long as we make some structural assumptions on the channel, we can do a good job. Right? And one interesting question that came out for me personally from this project was this idea of having an MMW-style algorithm for quantum channels itself. Right? I want to say a little bit about that. So this matrix multiplicative weights algorithm, for those of you who might not know, this is essentially giving Gibbs states as your updates. But this is also, in secret, the maximum entropy principle in disguise. Right? So where do these actually updates come from? They come from actually maximizing the entropy subject to some constraints. Right? And the constraints are essentially the values of the expectation values that you have up to that point in your learning procedure. So for me, it's an interesting question to ask, what could be a maximum entropy principle for quantum channels or quantum processes? And that's something that we just sort of leave open, but it's something that I'm still interested in thinking about. And if anyone wants to chat about that, or if anyone has any ideas about that, I'd be happy to talk about it. And with that, I'll thank you for your attention.
Thank you so much, Sumeet. We have time for one quick question. Yes, in the back. And Renato, can you come down while we're waiting?
Hi, thanks for a great talk. I was just wondering if you could expand on the non-Markovian assumption between updates of your online learning scheme?
Yeah, so I guess all that's really needed there. So that really boils down to how you define these operators EI. So what's going to happen is the actual value is going to still have this kind of inner product form. The only thing that will change is the constraints that this this operator E satisfies. But from the perspective of the online learning procedure, this is not actually so important, and actually we expand on this in the paper. So as long as your unknown channel is known to be a convex combination of known processes of this kind, which could be non-Markovian, then our results will apply. Because then all you really need to do is learn that unknown convex decomposition, those unknown probabilities.
Okay, just a quick follow-up. So if I have some channel that represents non-Markov noise in an experiment and it drifts between updates, would that be an issue, or is that something that we just average over as being part of the unknown channel?
So I think, I'm not sure, but I think in this case, it would just mean that your definitions of N1, N2, and N3 would be appropriately defined to take into account this drift.
Okay, thanks.
Yeah.
All right, thank you. Let's thank Sumeet again.